Hi everyone, and welcome again to this lecture. Just to refresh your memories, in the last lecture I went over the effect of elementary row operations on the determinant of a matrix. Now in this video I want to go over the determinant of elementary matrices. So to remind you what is an elementary matrix, an elementary matrix is one row operation away from the identity matrix, and that's how we can find out what is the determinant of an elementary matrix and what are the possible values of the determinant of an elementary matrix. So let's start. First of all, I recall the determinant of the identity matrix is always 1. And so if we take I and we permute two rows, or we interchange two rows, then we're going to get an elementary matrix. That's the first row operation. So we know the determinant when we permute two rows. We learned about this in the last video. The determinant becomes negative, so, or the opposite sign. So the determinant of I, it's going to be minus the determinant of E. So we know the determinant of I, or the identity matrix, is 1 equals to negative E. So the determinant of E will be -1. So that's one possible value of the determinant of an elementary matrix. Number 2, when we multiply, it's multiplying a row by a constant. So if we take the identity matrix, multiply a row by a constant, we get an elementary matrix. And we know that the determinant of I is going to be 1 over alpha times the determinant of E, and alpha being the constant, as we saw in the last video. And the determinant of I is 1 equals to 1 over alpha. So if I isolate the determinant of E, I get alpha. Alpha can be any constant. So the determinant of E so far, then an elementary matrix, we know it's -1, or it's going to be just a constant. Next row operation, when you multiply a row by a constant and add it to another row, and you change that row, the second row, and you get another elementary matrix. And we learned in the last video, when we do that, that operation does not change the value of the determinant. So the determinant of I is going to be equal to the determinant of E, and this is 1. So the determinant of E will be 1. So kind of giving you the summary of this, of the three operations. So the first operation, interchanging two rows, the determinant is going to be -1, determinant of the elementary matrix. When you multiply by a constant, a row by a constant, it becomes, the determinant is going to be that constant. And when you multiply a row by a constant and add it to another row, the determinant does not change, therefore stays 1. Very important note: the determinant of an elementary matrix is never 0. So please remember that. So now there are a couple of theorems here, and let me go over those two. The determinant of an elementary matrix times A is the determinant of E times the determinant of A. In this case, A is an n by n matrix and E is an elementary matrix. So type 1, when I say type 1, this is the row operations always. Type 1 row operation, when we interchange two rows, then the determinant, then the matrix A becomes B, and the determinant of B is -1 times A, because the sign of the determinant changes. So we know that if we do the same row operation and we get from I and we get the elementary matrix, in this case the determinant of an elementary matrix is going to be -1. We just saw that. So the determinant of B is the determinant of E times A, and when you interchange two rows, you get the determinant of B is E times A, or the matrix E, you can also write that as E times A. So that's multiplying the left side of A by the same elementary matrix. So the determinant of B can be written as the determinant of E times A, and that can be written as the determinant of E times the determinant of A. Type 2, and type 3, they work the same way. Please double check that on your own and to see this is true. Now there are other ways to prove this, and I let you go over the notes and different ways of proving this. So, however, let's go over this. There's a corollary. Corollary is just a small theorem. So if you have the product of elementary matrices times A, you can separate all of them and write this for the determinant. And write it like this, write it like that. So there's a theorem. If A is invertible, if and only if A, the determinant of A is not equal to 0. Remember that, please. Little proof. So one way, if you go one way, we assume that they have an inverse. So when we have an inverse, we learn that A can be written as a product of elementary matrices. And I wrote that. So we can write the inverses of that. We learned that in the last videos. Or if you don't want to use, because the inverse of elementary matrices are themselves elementary matrices, so you can just write it like that, E1, E2 times EK. So A can be written as E1 times E2 times EK times IN, you can just add it there. The determinant of A is going to be the determinant of that, and A can be written as the determinant of E1 dot 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 times EK times 1, because if you separate them, so we learned we can separate them. So times 1, because the determinant of I is 1, and we learned that the determinant of the elementary matrices cannot be 0. So therefore, if the determinant of A is 0, then the matrix is not invertible. So now there are other types to prove that. So I let you read the notes and go over this. You can also do that by contradiction. So please go over these steps and you're gonna see. So now let me go over the properties of determinants. When the determinant of A plus B is not equal to the determinant of A plus the determinant of B. The determinant of A can be found by expanding along any rows or columns. So therefore, if a row is consists of all zeros, then the determinant of A will be 0. If a column consists of all zeros, then the determinant of A will be equal to 0. Number 3, if one row of an A is a multiple of another row, then the determinant of A will be 0. So if one row is the scalar multiple of another row, or same thing for the column, then the determinant of A will be equal to 0. And these row operations, I put the summary. When you multiply a row by a constant, then the determinant is 1 over alpha, alpha being the constant, times the determinant of B. Or you can say the determinant of B is alpha times A. When you interchange two rows, you change the sign of the determinant. When you multiply a row by a constant added to another row, then the determinant stays the same. This is basically the summary of what we did. Pretty straightforward. The determinant of the identity matrix is always 1. So let's see. Here, if A is invertible, the determinant of A cannot be equal to 0. If A is singular, then the determinant of A is 0. So to show, one way of showing if there is an inverse, you can right away find the determinant of the matrix. If it's 0, then you can say it's not invertible. So if A is invertible, then we know A can be written as a product of the elementary matrices. So that's another way of showing that. And the determinant, as we saw in the last proof, the determinant can be written as the determinant of elementary matrices. They're never 0. So that's why the determinant of A cannot be equal to 0. If A is invertible, when you write AX equals to 0, the homogeneous system has a unique or the trivial solution only. So now let's look at this term. If B times A equals to I, then B is an n by n matrix and A is also an n by n matrix. Then A is invertible and B is its inverse. The proof, B times A equals to In. We know when that happens, B will be the inverse of a matrix. If I write AX equals to 0, show that has the unique solution. So let's start. AX equals to 0, that's the homogeneous system. If we multiply both sides by B, B times A equals to B times 0. B times 0 is going to give you 0, and then B times A, we know it's I, so In equals to 0, that means X equals to 0. That's the only solution, and that's the trivial solution. So another way of showing this, A times X equals to 0 has only, we assume has only the trivial solution. A is invertible. Now we have to show that B is A inverse. So we can start by saying B equals to B, then multiply by In. One side, B equals to B times I, and I can be written as B times A inverse. So then we learned this BA, if this is the inverse of that, BA is going to be In, and B equals to A inverse. So we see that B equals to A inverse. That's another way of showing this. Next, if A and B are n by n matrices, the determinant of AB equals to the determinant of A times the determinant of B. Little proof for that. Case of A. So case 1, we say A is invertible. Therefore, A can be written as the product of elementary matrices. So you can write it like that. So I is our elementary matrices. The determinant of A times this is A times B, and we can write that as the determinant of the product of elementary matrices times the determinant of B, and basically equals to the determinant of A times the determinant of B. If A is not invertible, then we know that the determinant will be 0. A is singular. So if A is singular, then the product will be singular also. We learned two matrices are invertible, then the product will be invertible. So the question is, what's the determinant of AB? So the determinant of AB will be equal to 0 because AB is singular. The determinant of A equals to 0. So the determinant of A times B equals to the determinant of B times 0. AB equals to 0. Therefore, the determinant of A times the determinant AB is also equals to, it will be equal to 0. The determinant of the inverse matrix, the determinant of the inverse can be written as 1 over the determinant of A. Little proof, A is invertible. There is an inverse. A times A inverse is In. The determinant of that, the product equals to the determinant of I, and we know that's 1. and we learned we can separate those. Determinant of A times determinant of A inverse equals to 1. Therefore, the determinant of the inverse, if you isolate that, is 1 over the determinant of A. And I think that's it for the video. So these are what we did. We went over the determinant of elementary matrices and the properties of the determinants. In the next video, what I will do is talk about application of the determinants. Thank you for watching. Please watch this couple of times and go over the notes so you can understand those much better. I'll see you in my next video.